Then it is a Tuesday here, the 22nd of July from Chico, California, and over here you see the moon. That's to let you know you're at an astronomy site. Well, you'd never know it recently because we're studying quantum mechanics and we're actually drilling down to the quantum. But you have to be more specific. There's more than one quantum. Now, in order to get to our solution, which I claim to have solved mathematically and geometrically, but it also has to be physical, so I'm going to show it to you. What is the quantum, for instance, of gravity? Well, I mean, everyone wants to know what that is. That's what everyone's looking for, because it would lead to the unified field solution. Gravity is not quantized as far as anyone can tell, and therefore it's a force that does not fit into the current model, which you could disregard the weak force and strong force. There are only two forces with which we need to be concerned now until we can get to the proofs concerning what is a force, because there's a violent disagreement over what is a force. It has a lot to do with gravity, which is not considered to be a force by exactly half the physicists and mathematicians. They say, Dr. Sabina Hassenfelder is one of them, oh, gravity is not a force. And the other half of all mathematicians and physicists say that gravity is a force. So which is it? We'll show you. So I have some new technology here we're going to use. We're going to begin with what is called, and we're going to study this, and I'll bet you can guess, Euclidean. What does that mean? That's what we're going to study first. Non-Euclidean what? Well, it's actually more than one thing because geometry is associated with mathematics. But the way it's always stated, and nothing wrong with this, non-Euclidean geometry. That's what I do, is geometry. So of course I've been studying non-Euclidean geometry for a long time. And we're going to start with a Wikipedia lookup, which I believe you're going to enjoy, because it's a lookup on a question which everybody asks who's interested in spacetime. Is spacetime non-Euclidean? That's a very tricky question to answer, but it has a standard pat answer, which AI Overview offers. So I'm just going to read this quickly. Yes, spacetime as described by Einstein's theory of general relativity, GR, is non-Euclidean. This means that the geometry of spacetime is not flat like a plane, but rather curved and warped by gravity. Here's a more detailed explanation, says AI Overview, apparently a member of the chatbot family. I'm quite grateful to AI Overview, although it doesn't have a soul, perhaps to Google or whoever invented this, because the first time I ever saw AI Overview, probably within days of its appearance, since I do research every day, I was amazed, and I just saw what it said because I was asking about spherical geometry, which I do regularly just to check and to extend my research, because spherical geometry has quite a broad base. But what I'm specifically looking for at all times, and have been for over 3 years now, does anybody have any insights into spherical geometry? So far the answer had been no, until about a little over a month ago, more like 2 months now, AI Overview in its first appearance on my screen, if it was there before I never noticed it, and I went, whoa, so I just read to see what it was. And it mentioned a term that I had never heard before, which really fascinated me because I try my best to know everything there is to know up to current cutting edge science, mathematics, however you want to phrase it, what is spherical geometry. Generally speaking, it's spherical trigonometry. That's what we're taught in school. But that's trig, which is 3 straight lines, translated to the surface of a sphere so we can compute spherical surface distances on the Earth. We're very good at that, but it is trigonometry. Spherical geometry is a bit ambiguous because of trigonometry, which has practically defined what spherical geometry is for over 2,000 years. But there are actually 2 forms of spherical geometry, one of which is unused, but it does have a name, and I just find this amazing. Even to the present day, I'm still rather flabbergasted that there is such a thing as intrinsic geometry. Well, now, of course, I've learned everything I need to know about that, well, to my present threshold, but I had never heard that term. I had already discovered what it is. That's part of my discovery. But I didn't know it had a specific name, called a class name or a type name. Because geometry is what? Is that just one thing? Depends on how you classify geometries. But you would probably say, no, there's more than one kind of geometry. So you have a definition for the class, which would embrace the definitions that are more specific. But intrinsic geometry, I knew of the dichotomy known in geometry called intrinsic and extrinsic. If you're a pilot, you've almost certainly heard of the difference, because if you don't know the difference between intrinsic geometry and extrinsic geometry, as you're learning to really, you have to learn in a plane to fly by instrumentation alone, that is, without the aid of vision. Well, I have just been amazed to discover that such an intrinsic term, such as intrinsic geometry, was simply unknown to me. I am an amateur and I do operate rather in isolation from the science community, so I don't really have an overseer, a professor, a guide. However, that should not be difficult to... I mean, if you're canvassing a field, you certainly would expect to know... Well, there is a reason why I didn't know the term. It's because it's strictly theoretical. And the only reason that that AI Overview knew about it at all is there is I'll just say a department of spherical geometry in advanced mathematical circles where they call what they're studying intrinsic spherical geometry, but it actually isn't. It's that they're pretending. And that's actually rather normal. I don't mean that pejoratively necessarily. So all right, that's enough for what we wanted to know about, is space-time non-Euclidean? Well, yes. If we just wanted a yes or no answer, we've got it. But I don't think that's enough, is it? It certainly isn't enough for me. So let's just see what AI Overview has to say here. In Euclidean geometry, which is the geometry of everyday life according to AI Overview, and it certainly would know, it's a series of electronic circuits. So it knows all about everyday life. Space is assumed to be flat and infinite. Now, any child who's looked into the night sky, which is every child, has wondered if it's infinite. So it is an assumption. Now, to be flat is a little different. I don't think we assume that space is flat. What we must assume from our visual perceptual system is that we see a flat screen image. That has been proved by physiologists, although you can prove it to yourself just by looking at this image on the screen, which is a flat screen image. But you literally cannot tell the difference to a threshold. whether that's actual, we're in the same room or not, or if you're just seeing a flat screen projection of what you see on the screen. The latter is true. And we see everything that way, although in the case of the physiological aspect, we see in two different ways that we've learned to make simultaneous, and that's quite a mouthful. There's actually a lot of profundity in that. Well, we're going to get into all that, and what is the goal here? We would like to know something about the parallel postulate and why that led to non-Euclidean geometry. What is non-Euclidean geometry, and how does that apply in my research, so that we can apply my research, which is pure geometry, with a mathematical component, quite simple, actually simpler than linear algebra or linear geometry, is spherical geometry. And we want to know how that applies to the Bošković force curve, into which you're going to be seeing some amazing, I trust as amazing to you as it is to me, some absolutely astonishing direct insights into the geometry of reality, which is what science is trying to achieve. All right. So in everyday life, space is assumed to be flat and infinite. That's a reasonable compound statement. Although we're going to be talking about that because that's not necessarily true. Is space infinite? That's a yes-no question. And is it flat? Well, first of all, we have to know what's meant by that. We'll get into that so that you know. The beginning of science is simple knowledge. What are the definitions? What do things mean? Then you have to put it together. Well, that's called science. Include parallel lines never intersecting. Euclid's fifth postulate. We'll be talking about that a bit. So we can finally, you and I, understand together what in the world is so important about that postulate. It actually is quite significant. But it's difficult to see how. Because aren't there such things as parallel lines? Not in Lobachevsky or Bolyai space. And don't worry, you're going to know exactly what these things are, perhaps for the first time. And don't ever think you know everything. There's always more to know, and believe me, I've learned that, your face can get red. Just be aware, be humble. All right. And the sum of angles in a triangle always equaling 180 degrees. Well, we already know that if you draw a triangle, like from the North Pole, that's one apex, or vertex, and then you draw two orthogonal lines that go down to the equator, so now the distance is 1/4 of the circumference, which is the equator. Do the interior angles sum to 180? No. All right, so we'll find out what that means. Because that is actually non-Euclidean. Why? Because they're not straight lines. That's why it's non-Euclidean. But there's more to it based on, I'll just say, the progress of science, which is, obviously, since it's progressive, we're not getting everything right until we progress and then look back and say, boy, was I naive? Well, that's, in a nutshell, what science does in terms of progress. You can't get everything all at once. We had to start with Euclid. To say non-Euclidean is not to put Euclid in his severely primitive Bronze Age place, although I have stated such in certain contexts because it is true. But on the other hand, Euclid, in a sense, is practically already, you don't want to say immortalized because that's kind of, I don't know, you might not mind. These days you can say almost anything, nobody cares. All right, in non-Euclidean geometry, these rules, that is the interior angle sums to 180, that's one rule. Not in non-Euclidean geometry, it can be more or less. By the way, do you know if it's more or less on a spherical triangle? We'll find out, but I just wanted you to guess because it's a good mental exercise, which I would typically get wrong because for whatever reasons. But don't ever be afraid to guess. This is not a beauty pageant contest, and we're not trying to get more and more money at the expense of some other poor Joe who's not as smart as you. We're not industrial scientists here. We don't do anything for money. Now, it's up to you whether you want to. I might, but not yet. Because I don't believe it makes you biased. If you're getting money from a source, that source may tell you, well, this is the model we work with, don't work with any others, or we won't give you any more money. That defines a lot, but let's not go there. All right. These rules don't apply, including the parallel postulate. That's really what we're driving at. Our two lines always have only one parallel aspect. In other words, if you tilt either line, they're going to intersect. What if they never intersect? That's called parallelity. And it's interesting the way Euclid defined that, because he never used the word parallel. He was talking about intersecting, but it directly implies, what if the two lines don't intersect? And that's called the parallel postulate. All right. In non-Euclidean geometry, these rules don't apply. Space-time, as described by general relativity, is non-Euclidean because massive objects warp the fabric of space-time around them, causing objects to move along curved paths, which we interpret as gravity. Yes, we do. Next item down is Minkowski space-time. That might be a baffling term to you, or some kind of cryptic. It certainly was to me for a long time. And so, some of these things you have to look up more than once. I do. In the absence of gravity, or in a region far from massive objects, such as the sun, spacetime is described by Minkowski spacetime, which is flat, but not Euclidean. Interesting, yes? What could that possibly mean? We're going to find out. The key difference is that the distance formula in Minkowski spacetime includes a time component with a negative sign. That is a negative signature. The entire it's a 4 vector, with one of the component numbers signed negative. That's what's being said here. That's because if it were positive, it would be spatial, which is not space-time. And since it's not actually the same data type, time is a different data type, it's temporal instead of spatial, it must be signed negatively in order to maintain orthogonality. That could be considered negative instead of positive, but they're still orthogonal. And that's what Einstein proved, is that time, well, one of the things that he proved is that time can be considered to be orthogonal to space. That is so incredibly profound that nobody has actually seen the full profundity of it to a new threshold, such as I did in 2022. I've canvassed the field for over 3 years now, and it's true. I just happen to know I'll just say an integral form of Einstein's field equation, which is based on the orthogonality, 3 positive spatial, 1 negative temporal, all orthogonal. Time is obviously imaginary if it's negative, and that's spacetime. Is it Euclidean? No. Is it curved? Minkowski spacetime is not curved. So that's what's being said by AI overview, and that might baffle you. Don't let it baffle you. It's just that you have to describe each of the things until you can put them together and see what all this means. It does mean something. You're going to see it today. That's part of my goal, is to help us both see this better. Isn't that the whole idea? Part of it. The key difference is that the distance formula includes a time component with a negative sign, unlike the Pythagorean theorem used in Euclidean geometry, which is all positive. They didn't have negative numbers or negative direction in the time of Euclid. That was much later. All right. Curvature, continuing, and we're almost done. The curvature of space-time, obviously not Minkowski space-time, it just said that's not curved, it's flat. But the curvature of space-time, non-Minkowskian, is directly related to the distribution of mass and energy, which are equivalent. Just think of it as mass, but Einstein included energy. Regions with more mass have a greater curvature in space-time. Okay, so there is curvature. Wow, that's what we're going to find out. All right. I hope you're having fun. I certainly am. This should be fun. You're not practicing for an exam or to save your life by getting government money. You're doing what a rational full-grown man does to answer the blueprint that heaven put into your soul. Okay. All right, to put this all together so we know what we're doing, we're heading for the Bošković force curve. But in order to lay the groundwork for some amazing insights, which I hope to share with you, I'd like you to know how it came about that we got non-Euclidean geometry, which has a lot to do with what you see here, because obviously that's non-Euclidean. There are no straight lines. It's actually based on a circular plane, which is not what Euclid axiomatized. So it is tantalizing to think about how this might have something to do with a parallel postulate, which Veritasium will now explain in a way that I think, well, he's a gifted presenter. I really like Veritasium's channel. I strongly recommend it. This is from 1.5 years ago, so it's late 2023, actually October, entitled How One Line, this is a line of text, so there's two meanings of line right in this case. How one line of text in the oldest math text hinted at hidden universes. This is about our hero, János Bolyai, a Hungarian mathematician of the mid-19th century, who is well recognized now as having changed geometry forever. And there are two other names intimately connected with this Hungarian genius, whom believe me, I admire this man. There's no mistake to admire János Bolyai, whose father, Farkas Bolyai, knew Gauss, who is the other of three names, and there's one more, a Russian. Contemporaneous, this is not unheard of, but there was a simultaneous discovery of this miraculous breakthrough in geometric insight. Virtually simultaneous. In Russia, in a city called Kazan, where a man was working on non-Euclidean geometry having to do with Euclid's parallel postulate. And he discovered essentially the same thing as Bolyai, who was in Hungary. In Transylvania, if you want to know. So it was part of the Austro-Hungarian Empire. So a lot of the titles of works at that time it says Austria, but it's Austria-Hungary. All right, so let's listen to part of this. I'm sure you're going to enjoy this. But I just know that this man is going to be able to summarize it. I've already listened to it, of course. He's going to do this much better than I could. And it's just enjoyable. So I hope you like this. It's making sure we have sufficient volume, and here we go. This is about 9.5 minutes into a half-hour presentation by Veritasium. 18 million subscribers. Close to 15 million views of just this video.
This is known as the Poincare disk model. Here, straight lines are arcs of circles that intersect the disk at 90 degrees. And just like on our original shape, a straight line down the middle appears straight.
That's very profound.
Straight lines next to it appear to curve away.
What's remarkable is that Bolyai didn't have a model of hyperbolic geometry yet. He was just drawing Euclidean triangles with the assumption that Euclid's fifth postulate didn't hold. And while Bolyai found that the behavior in hyperbolic geometry is very different than Euclid's, mathematically it seemed just as consistent.
In 1823, the 20-year-old János wrote to his dad, "I have discovered such wonderful things that I was amazed. Out of nothing, I have created a strange new universe. But Bolyai had been doing more than just tackling ancient math mysteries. In his 20s, he joined the army, where he continued developing two of his other passions, playing the violin and dueling. He had mastered both, but with a sword in particular, he was unmatched. Perhaps because of his many talents, Bolyai grew arrogant and found it difficult to accept authority from his superiors. That made him hard to get along with. This reached a peak when, during one of his deployments...
Can I skip ahead here?
His father's textbook. Extremely proud and excited about his son's work,
Farkas
Bolyai sent it to perhaps the greatest mathematician of all time, Carl Friedrich Gauss. After careful examination, Gauss replied a few months later, "To praise it would amount to praising myself, for the entire content of the work coincides almost exactly with my own meditations, which have occupied my mind for the past 30 or 35 years." Years earlier, Gauss had wandered a similar path. In 1824, he wrote a private letter to one of his friends in which he describes discovering a curious geometry, one with paradoxical and, to the uninitiated, absurd theorems. For example, Gauss writes, "The three angles of a triangle become as small as one wishes, if only the sides are taken larger.
Hyperbolic
Yet the
geometry.
area of the triangle can never exceed a definite limit." In other words, you can have a triangle that's infinitely long, but the area is finite. You can see why by using the Poincare disk model. A small triangle looks pretty ordinary, but as you make it bigger, the angles start to become smaller and smaller. Eventually, all those angles go to zero, because all these lines intersect the disk at 90 degrees.
Okay, I don't want to overburden us with one single avenue here. So we're going to curtail that, but if you want to look it up, you certainly can. It's from October 2023 at the YouTube channel Veritasium. It's called How One Line in the Oldest Math Text Hinted at a Hidden Universe. Alright, I beg your indulgence here, but this is very well thought out. Well, from my point of view, I've thought this out several times, how to present this, because this is actually a shock to the whole mathematics community. I'm giving you the high road to understanding this, because we've had, a century and a half, I'll say, roughly, to mull this over as a community of scientists. We know a lot more. Certainly I do, because I actually have more insight into this than any mathematician yet. That is the nature of my discovery. I'm not trying to be pretentious, precocious, or preposterous, or pompous. the 4 Ps. But I want to read this verbatim. I know it's going to be difficult for you to read this. I only have it up to show you what I'm reading from. So I'm going to go through this quickly. Please, this is not actually complicated. But it is a bit complex, which means there are several relationships that I'm bringing together, so you'll have a direct insight into the greatest discovery in the history of mathematical physics, sometimes called physical mathematics, but it's a combination of physics and mathematics. I made this discovery 3 years ago, so I'm publishing now. I'm showing you what I'm about to publish, but it's hard to lead up to. And to get to it, we're going to go with Roger Bošković, who lived 2.5 centuries ago, is when he made his discovery. It shows up in the strong force, nuclear force curve, which is in Wikipedia, representing the cutting edge of particle physics today. I deal separately with the standard model, which is quite a different zebra of a horse, I'll just say. So the parallel postulate, according to Wikipedia, in geometry, it is the 5th postulate in Euclid's Elements, and a distinctive axiom, actually the 11th axiom, in Euclidean geometry. It states that in two-dimensional geometry, here's a quote from Euclid, if a line segment intersects two straight lines forming two interior angles. Here are your two. This is easy to fumble at, okay? If a line segment intersects two straight lines, it doesn't say the relationship of those two straight lines. So just two straight lines, and a line intersects them both, then the interior angles less than two right angles, then the two lines, if extended indefinitely, meet. In other words, if the line cutting the other two lines sum to less than two right angles, so in other words, the line that's cutting across the two lines is not cutting across them such that it's orthogonal to the two lines. It's at an angle. If that's the case, then you can measure the two interior angles, and if it's less than two right angles, it means that these two lines must intersect. So you can see it goes about it completely ass backward. I should say
ass posinorum backward.
Because if these two lines are parallel, he doesn't say if there are two lines parallel or not, that you can prove from that by the interior angles that you can add together after cutting the two lines, whether they're parallel or not, with another line, you can add up the angles. And if it doesn't add up to 180 degrees, it means these two lines intersect. So there's a special case where they don't intersect. And that's when the straight line that cuts across them makes two right angles. So it does sum to 180. And therefore, that means these two lines are parallel. So in the parallel postulate, Euclid never uses the word parallelity, and he doesn't even imply it. You have to, unless you consider it is geometrically implied, but you have to work that out yourself. Nowhere in this statement, which is the fifth postulate, nowhere does he talk about parallel lines. So it's a remarkable. And so I'm just going to finish this article, and then we'll cut this off at 40 minutes, because I don't like to go over 40 minutes. We'll have another presentation this evening. It's mid-afternoon here in Chico on Tuesday, the 22nd of July. This postulate does not specifically talk about parallel lines, and there is a note to that. So you can look that up, non-Euclidean geometries. But Wikipedia is very good about referencing its sources. It is only a postulate related to parallelism. Euclid gave the definition of parallel lines in Book 1, Definition 3, just before the 5 postulates. That may interest you or not. It does not interest me, because I'm not interested in linear geometry, because I've transcended it with the correct geometry that science will now adopt, or it won't progress. I know, but that's what I discovered, and that's why I make these videos. Because I have to make I've made over 1,025 videos in 3 years to practice for writing my paper and be prepared to give lectures, presentations. I don't look for money, but after 3 years of this just expanding in all positive directions, I may be forced to ask for money, because Americans, I'll just say maybe people in general, tend not to credit what you're offering unless you charge them for it, showing that it must have value, or why would you ask for money? That can backfire, of course. The postulate was long considered to be obvious or inevitable, but proofs were elusive. Eventually, it was discovered that inverting the postulate gave valid, although different geometries. We're leading up to non-Euclidean. A geometry where the parallel postulate does not hold is known as non-Euclidean. You can see that's quite a stretch. It's really not non-Euclidean. It's non-Euclidean parallel postulate geometry. Otherwise, it's still Euclidean. Now, geometry that is independent of Euclid's fifth postulate, that is, it only assumes the modern equivalent of the first four postulates, is known as absolute geometry, and Bolyai uses that term. And he actually uses it in a different way than is used here. But here it is also synonymous for what is known as sometimes, although I've never heard this, neutral geometry. So all of a sudden in the 19th century, we find out from Bolyai and Lobachevsky, and Gauss too, that there is a different kind of geometry than had been used for 2,500 years. So you would have to say that's a major turning point. It leads to spacetime, by the way. Probably the best known equivalent of Euclid's parallel postulate is Playfair's axiom. Now, Playfair's axiom simply is a restatement so that it uses the word parallel somewhere. So this is Playfair's axiom in a plane, given a line and a point not on it. At most, one line parallel to the given line can be drawn through the point. That is not exactly, but virtually equivalent to Euclid's fifth postulate. But the way Playfair says it enables the parallelity aspect to come out. But it's not exactly the same. And it's amazing on these seemingly very minor or delicate points. So much can depend. And we don't want to go down that rabbit hole. But you do need to be aware of what these men faced as they encountered a brand new geometry. All right, so to go back to our parallel postulate, and then we'll close this out at 40 minutes. You'll see, well, you know what? That'll be your homework because we just reached 40 minutes in just 30 seconds. So we'll be back this evening with a follow-up. This is the third in our lead up to the Bošković force curve, on which I'm the world's foremost expert now because I know how to read it. It is demonstrated in the strong force curve called the curve of nuclear binding energy, which ties two protons together and eventually up to 100, technically up to 119 protons. So stay tuned. Wherever you are in the world's time zone, we'll be back later. Thank you so much for tuning in.